Yeah.
Yes, I do. It looks magnificent.
Okay. Right. So just a quick start. Of course, the background of this first slide is the new James Webb deep field image. So that is really exciting. Last time I gave this talk, the James Webb wasn't up yet, so it's exciting. Okay. Oh. Okay, so it's going to be a long talk. If you want to slow me down, slow me down. If you want to interrupt, that's fine. I don't mind. But I'm going to talk. I need to give a bit of background on galaxy properties, where they live, and how we observe them. Mainly talking about the different wavelengths, and so on, and how they evolve. So let's start from an easy definition of galaxies. This is the definition that I just found on the dictionary. It's a system of billions of stars. Then there's gas, dust, and gravity is what keeps it together. However, the definition doesn't mention dark matter, which is a fundamental component of a galaxy. And these are familiar to everybody. The three main types of galaxies: elliptical, spiral, and irregular. And these are all optical images, and we can already infer a lot just looking at these. First of all, the structure. Ellipticals are like a big sphere, or spheroid type thing. Can be longer, oblongate, but yeah, that's the general shape. Spirals have similar shape in the middle, and then they've got the famous spiral arm, sometimes a bar. And then we've got all the irregular galaxies, which don't have any clear structure, but they have other things in common. For example, ellipticals are mainly made of old stars, and so are the centers of spiral galaxies. While irregular galaxies and the spiral arms are usually made of young stars, because the star formation is still ongoing. And in fact, for star formation to happen, they have to have dust and gas in them as well. We also can tell quite a lot about the way the stars move in galaxies. So we've got random motion, so motion in all directions in ellipticals, in the center of spirals, and in irregular galaxies. And then we got a rotational movement on the arms, in the arms of spirals. I kept the lenticulars out because they are kind of an in-between. And often many lenticulars with new telescope, we've observed that they actually have arms anyway. So let's leave them out. As you probably know, Hubble is the first person that observed a galaxy. Well, he identified a galaxy as a galaxy. Before, they just thought they were nebulae inside their own galaxies. So he identified them, coded, let's say, their structure in this fork diagram. And also, thanks to this amazing graph, people said, oh, well, that is giving us an evolution, because surely if I start as a spheroid and then for some reason stars start to rotate, then the rotation leads to a flattening, and then probably in some ways, again, the arms form. And so they called spiral galaxies late type galaxies, and ellipticals early type galaxies. These names are still used today, despite us knowing that this was completely wrong. And actually, galaxies evolve in the other way, in the other direction. So we got spirals forming first, and then through going through mergers and other events, they turn into ellipticals. Yes, because galaxies evolve. They evolve because they are made of stars, and stars evolve. They evolve because they have active galactic nuclei, which in some ways can influence their evolution. And they also evolve because they're not alone. Well, again, I just leave the slide to you. I'm not wasting too much time on this, but you know how stars evolve. Stars evolve not only in themselves, as in from burning hydrogen to helium and to heavier elements, but also when they explode as supernovae or other events, they also make the surrounding evolve because they enrich it with heavier metals. So the gas and dust that are used to form star after a star explodes, for example, they are changed, they're different because they have different elements in them. And so this happens, star formation, supernova explosion, they push a material outside the galaxy, and then the material falls back into the galaxy to form new stars, and so on, until the gas runs out. And as we said, they change the intergalactic medium, so the space around them, which was originally made of hydrogen and helium. When stars or the medium gets metal enriched, we say that its metallicity increases. Yeah, so that's absolutely, that's fundamental for the evolution of galaxy, the state of this intergalactic medium. And so are the AGNs. So AGNs are active galactic nuclei. What causes them is, so every galaxy we know has a massive, a supergiant black hole in the middle. Not all are active though. So some don't have material close enough to them to fall in, and so they are like dormant. But if there is material to fall in, when this material falls in, it just creates emission in radio, X-ray, and other things. And these are very powerful events which can disrupt sometimes the shape, but definitely the distribution of gas within the galaxy, usually leading to ceasing the star formation. Because, so essentially what happens, this is the galaxy in the optical, this is the radio bubbles, and the X-ray is the gas around it, and this is a composition of the three. So what happens is that these bubbles literally push away the gas from inside the galaxy, and so there's no more gas for star formation. But as I said, galaxies are also not alone, because they live in the large-scale structure of the universe, which kind of looks like this. So this is a simulation, but each dot is a galaxy, which means that where the dots are constant, where it's brighter, there's lots of galaxies. Well, this is a real plot of the galaxies measured by the 2DF survey, showing that the galaxies are essentially uniformly distributed in all directions up to a certain redshift. This is a quite old survey, but I mean, it's still one of the best ones we have anyway. When you see that it looks like they're empty, is some instrument limitation, so it's not, these lanes, for example, are not real. Yeah, so we know the universe is a big place, there's a lot of stuff in it. This is the cosmic microwave background, which kind of tells us what's the distribution of mass around. And we can see it's quite uniform, considering that the red and the blue, so the maximum fluctuation in density is 10 to the minus 5, so 0.0001. That's the difference. So essentially it's uniform, and thanks to this we could infer what's inside our universe. Ordinary matter, which is us and our stars and planets, is 5% ish. Dark matter is 26, 27, and the rest is dark energy. As I said, dark matter is fundamental in the description of a galaxy, because there's more dark matter in a galaxy than luminous matter. And the first time we suspected there was something else, not just visible matter, is when we measured the rotation curve of a galaxy, which we expect would increase up to the edge of the galaxy and then start decreasing the further away from the galaxy we move. And instead, the observation showed that this curve is flat here, so suggesting that there is some mass here that we don't see. And this is the same mass that you probably hear me use this word. It's what causes space-time to bend, because it's like a mass on a heavy mass on a sheet. It makes like a well, and things fall into it. That's kind of gravity effect, and this is what we call gravitational potential well. Right, so what is dark matter? Recently, probably every other day, a paper comes out that says, oh yes, we think it's definitely dark matter, it definitely works. And 2 days later, there's a paper saying, no, it's the physics that's wrong. So I don't know. The belief at the moment is that it's a particle or a group of particles called WIMP, weakly interacting massive particles. So they interact only via the weak force. And that's why it's dark, because it doesn't interact via the electromagnetic force. So we can't see it because, as I said, no electromagnetic radiation. It does not interact in any way with the matter we know. It's not antimatter, because otherwise we would see the result of matter and antimatter annihilate. And it's not black holes, because even if we can't really directly observe them, we still have means to measure their presence. But most of all, what's dark energy, which is the majority of what the universe is made of? Essentially, we don't know. For now, it's a constant in a maths formula. Based on that formula, we know how much there is, because we can observe how it affects the universe expansion, which is not constant, but it's accelerated. But that's it. We don't know what dark energy is. Right. So just the big picture, galaxies live in this universe that was created with the Big Bang. For a period, there was nothing, the Dark Ages, and then the first stars formed and the galaxies, and then the universe is the way we see it now. So we study galaxy evolution in this context, which is quite confusing. Right. One thing we seem to know is that we know how galaxies form. They merge. So first there is something small, and then gravity attracts something else that falls in, and this structure grows. Whether the structure is a galaxy getting bigger, or a galaxy attracting another galaxy and then forming a system, and then in some way these two galaxies will interact, but then other galaxies will have come to join them. Well, we know that's how the universe is formed. We got simulation, dark matter only simulation, that prove pretty well this theory. And in fact, given what we know so far, if we feed in what we have, we get a picture that really replicates our real universe. Yeah, so that was just an image in static, and this is how the simulation evolves in time. So this here would be a giant supercluster of galaxies. Right, again, this is just to give a little summary of how the universe formed: Big Bang, dark matter. So dark matter, for some reason, the density wasn't exactly uniform, so areas started to collapse, so because of gravity in the denser areas, and so on. And then baryonic matter, which is the visible matter, followed, and once the baryonic matter was there and it collapsed, the first stars formed, and then galaxies, and then galaxy clusters and group, and so on, and they keep on growing. However, the universe also expands. Right, so we talked about environment. Yes, so galaxies very rarely live isolated. Usually they live in groups or clusters. Groups are smaller, and clusters can be huge and can contain groups as well. This is the definition is not universal. Some studies slightly change the definition to reach their purpose, I guess. But usually less than 50 galaxies a group. The size is no bigger than 2 megaparsec. But what's interesting is that that's the majority of galaxies. So the majority of galaxies are in groups. The suspect is that it's even more than 55%. But anyway, we know that the majority of galaxies are definitely in groups. problem with groups and clusters is that they are very difficult to define because of the large scale structure, the filament structure. So these filaments are all galaxies that kind of join together different clusters, for example. So who's to say where one finishes and the other one starts? Especially if we consider that we don't have a super clear vision of the 3D distribution, because we know, well, we see obviously the projected shape in the on the sky, but we have the redshift, but the redshift is not as accurate as position. So we don't really have a well-defined 3D distribution. We live in a group. It's a local group. It's roughly 50 galaxies. Milky Way is split between 2 galaxies, so there isn't one in the middle. It's us and Andromeda. It's big, but it's big because it's easier for us to see galaxies belonging to the group because they're closer. And we are part of a supercluster called the Virgo supercluster. Right. So now we know what galaxies are and galaxy groups and galaxy clusters, but how do we look at them? And here is the multi-wavelength, where the multi-wavelength issue comes in. So optical, you probably look at the stars more than me at the moment, but we see them with telescopes, we see the stars, we see the light, we see some dust if it covers the light, nice dust lanes on Andromeda, but that's it really. With that light, if we take specific measurement in using different filters, we can infer the magnitude and the color. So the magnitude, well, when we talk about apparent magnitude, that has to do with the eye, and it's always a positive number. The smaller it is, the brighter the galaxy, and it depends on the distance, though. So it's not a very scientific measure. But we've got the absolute magnitude, which for galaxies is always negative. And again, the smaller it is, the brighter the galaxy. So for example, a galaxy is -20 or more, or less. The brightest known star is -10, and our sun is around 5. And the color, well, the color is, so when we use different filters, we can get the magnitude in different colors. And if we take the difference between 2 colors, we can infer how red the galaxy is. When a galaxy is red, when the stars in it are old. So that's a quite useful measurement to start and study a galaxy a bit more. And we can draw these nice plots. This is absolute magnitude, and this is a color. And we see that there is a cloud of red galaxies, and then the star-forming galaxies are below. There's quite a neat separation. And then there's the green ones, which are, well, for different reasons, they don't fall in either. But the separation is quite neat. So this is used a lot to decide in what category to put a galaxy. Right. So what do we observe if we observe in the UV or in the infrared? Well, the UV shows us the star formation. The example is here. This galaxy in the optical could seem a quite distant elliptical galaxy. But if we look at it in the UV, we can see the spiral arms, which is where the star formation is happening. However, if the arms are very dusty, we wouldn't see them in the UV. We would need the infrared, because the infrared observes the radiation emitted by heated dust. So the star is formed, it's very hot, hits the dust surrounding it, and we see the infrared. When we observe clusters of galaxies mainly, we also observe in the X-ray. So the X-ray gives us the temperature of the intergalactic gas. So of course, this is a superposition image. So we've got the optical, and the purple is the gas. The gas is very hot at the center of the cluster, and then it cools down, going out. And this is an indication that this is a real cluster. So it's a real structure that's gravitationally bound. So the galaxies are really interacting in a way or another with each other. In a weird way, we can also observe, not directly, we can observe dark matter. And we can do that by measuring the mass within a group or a cluster of, mainly a cluster of galaxies. We can measure the mass given the galaxies and their velocity. So the purple is still the gas, so the X-ray, while the red in this case is the dark matter. And interesting, especially in this cluster, the cluster in every other wavelength looks like it's one cluster, but because of these two separate lumps of dark matter, we discovered that this is actually two clusters that are colliding with each other, and they're still in the process of reaching equilibrium after they merged into one. But the most information really are given by spectroscopy. Spectroscopy is when when we talk just about light, is essentially what a rainbow does. Light through a prism splits because different wavelengths travel at a different speed, so they separate and we can see the rainbow essentially. So we can do that with starlight, and we get a nice spectrum like this, which is very neat. And this is a star spectrum. I think this is the sun. The height gives us the temperature, also the wavelength where it's center. You see how neat this is. We got the violet, it's a higher frequency, so shorter wavelength, while the red is lower frequency and so longer wavelength. Yeah, so this is what it does. So a spectrum, it doesn't matter what it is, has got some features. The main one is the continuum, which is the shape. For a star, it's a black body spectrum and only depends on the temperature. But then we've got absorption and emission lines. This again, this is a star. These are absorption lines because something is in the way of that light, and so that light doesn't reach us, or not as much. And then emission lines are often caused by gas in the way, not close. Like, so when I've got right, so the absorption caused by cold gas or dust, which can be either in the path of the light or on the star surface. While when the hot gas is in front of the star, it just gets heat up and emits just the emission lines. If you're interested, this is the atomic process that causes absorption and emission. We can talk about that later. When it comes to a galaxy, it's a bit more complicated because the continuum is the sum of all the stars in the galaxy. The absorption lines, again, are the sum of all the absorption lines on all of the stars, and also if there is cold gas or dust within the galaxy. And then we got emission lines, which are due to gas, like this nice oxygen one, gas which is either within the galaxy or on the way, so on the path of on the path that the light has to cross to get to us. But despite it being so difficult to understand because it looks messy, there are two key features which unfortunately are exactly in the same point. So they're useful, but they cannot easily be separated. And they are the 4,000 angstrom break, which is this big jump. And next to it, there's also the Balmer break. If the jump is very big, it's mainly due to the 4,000 angstrom break, and because there are old stars or stars with very high metallicity. The Balmer break is a bit is a bit more difficult to observe because it's due to stars with an intermediate age, which often are not found all together, so they might be more spread in the galaxy, so that it doesn't give an effect as nice as the 4,000 angstrom break. So if I see a spectrum with a big jump, I already know that's an old galaxy. Yeah, the problem with spectroscopy, as I said, is amazing, is the best way to get information about a galaxy. The problem is the time it takes. So just looking at the star, we can take a picture. This is a 20th magnitude star, so it's quite a dim star. But it's roughly, is very common, that magnitude for a galaxy. So if for a star it takes 10 seconds for a photo, it takes 15,000 for a spectrum. And so when we talk about the same process for a galaxy, it can take days. For example, the deep fields took weeks, for example, to take, and they're not even spectrums. We've got some spectrums, but yeah, so that spectroscopy cannot be done blindly. So we usually do photometry first, identify interesting targets, and then spend our time only on those, because it's so time consuming. But these are all the things we can infer from a spectrum. So the redshift, which is the distance, the type, as in it's an old galaxy, a young galaxy. We can see if it's an AGN. We can see if it's star forming. The kinematics. So, for example, if we're observing a spiral galaxy, we can determine what's the direction of rotation. We can see how dense the gas is in the galaxy. We can not only tell if it's a star-forming galaxy, but we can actually give indication of what percentage of star is what age, with errors, but we can do that. And same for the gas metallicity of the stars, and yeah, gas metallicity or chemical abundance of the star. Just again, if we can talk about this, just a quick slide on redshift. Redshift is due to the expansion of the universe. The universe while moving, so essentially, if a star is nearby, it causes redshift because of its movement, like an ambulance with the noise. And this is what happens to the line. So we determine redshift by looking at absorption lines, usually, because they move from their position in a lab or on Earth. And we can determine if the galaxy is moving further away or close to us, and by how much. But this is not necessarily due to the movement of the galaxy, but is due to the expansion of the universe, which is stretching the wavelength itself. So a ray of light, a wave moving through an expanding universe, gets stretched. So that's the redshift we observe. And we observe it like this, because something that would be at 1 micron, a feature that would be at 1 micron, if we move in redshift, goes towards longer wavelengths. And so the same galaxy would look completely different at a different redshift. And we have to do spectrums in the infrared to see very distant galaxies. The type, I said earlier, just by looking at the shape, this is a boring old galaxy with a big jump here, no emission lines. And then the jump gets smaller. There's a lot of absorption here because of dust, probably due to star formation. And then we have, this is definitely an AGN, because these emissions are usually due to the active galactic nucleus, not just star forming galaxies. Usually, star forming are spirals and passive are ellipticals, usually. We'll see that later. And then we got algorithms that allowed us to measure, well, as I said, this one shows us the rotation of a spiral galaxy. So this has to be a nearby galaxy. So this was a nearby galaxy. And we take the spectrum at different positions compared to the center. And then by plotting this, we can infer that the red side is because the spiral is rotating away from us, and the blue is rotating towards us. And so we know that the rotation direction of this galaxy is like this. the gas density is given by how intense these emission lines are. The velocity with which the galaxy is moving away or towards us sometimes is given by how broad these absorption lines are. And this is all done with an algorithm that takes some simulated galaxy spectra and tries to match with a real one. In the same way, that's how we infer the age, the metallicity, and the mass fraction. So, for example, this galaxy plotted here has got a lot of, well, the majority of its star in the disk anyway. It's quite young. And the metallicity is quite high. So 0 is solar metallicity. So this is more metal rich than the sun. And the bulge, as we can see, the stars are much older. And the metallicity, again, it's older than the sun. Interestingly, the disk has some low metallicity stars as well, because there's new gas accreted from outside.
Sorry, Melissa, what is mass fraction?
Oh, the mass fraction is given here.
No, what is a mass fraction?
Is this how much of the stars is that age, essentially?
Oh, okay.
Yeah, so it tells you if you have 100%, and it tells you it should add up to 100% of the galaxy. Right, the main problem we have here is the age-metallicity degeneracy. So one thing that is very difficult to disentangle is whether we're looking at a young galaxy that has a high metallicity, or if we're looking at an old galaxy that has very low metallicity. As you can see here, the ages are double, and still the two spectra are exactly the same. So sometimes we can try to distinguish between the two based on other things. But in terms of only spectral analysis, that's the most challenging issue we have. Right, there's the other problem. We have told you how to observe things, but what happens when we try to observe far away? Well, the observation of very distant galaxies started with Hubble. But again, it's a photo. And so using a technique that I'll explain in a minute, we can try to identify which one of these galaxies is really, for example, let's say this one is very red. Is it because it's far? Or is it because the stars for some reason are just very old, but it's a nearby galaxy? So if we think it's far, then we can spend time to do the spectrum. But otherwise, it's really not worth it. What's interesting, though, is that in that deep field, we have seen galaxies that don't exist anymore, anyway, not in that form, which is something that allows us to see back in time, essentially. That's what we're doing. We see what the universe was like quite close to the Big Bang. So the way, as I said, a spectrum moves with redshift. We are looking at galaxies that are young, and they are not what they're like now, but it gives us an indication of what the universe looked like before and how it can have evolved to where it's today. We need big telescopes, and as I said, we need to go into the infrared, as you probably know, given that the James Webb is mainly an infrared telescope. So to identify candidates at high redshift, we use a technique that's called a dropout technique. So we take just photos in different bands, and because a spectrum, can I go back? Yeah, because a spectrum at some point has a big drop anyway, which is not in the Balmer break. It's just a drop in the infrared. Because of that, we can take a lot of images, and when the galaxy disappears is because we caught that drop. So if we assume that's the drop, we know at what wavelength that should be, and we know at what wavelength these filters correspond, so we can infer a photometric redshift. and then with spectroscopy, we can confirm it or not. Another way, but we can't use it with all galaxies, is to look around big clusters and look at the phenomenon of gravitational lensing, which is when the galaxies behind the cluster, their light traveling through space, they get bent and also magnified because there is this big mass they have to go around because of the gravitational potential well formed because of this massive cluster. So they bend. So bending, though, we end up with multiple images of the same galaxy. So probably this one is the same as this one, and so on. Red one, there's just one. Oh, this one is probably the red one as well. That one's definitely the same one. So we got multiple images, and these galaxies wouldn't be visible with the same exposure time if the cluster wasn't in the way. So these are the two techniques we use to look at distant galaxies. So until before 2010, we didn't get to 8, and just recently with James Webb, we got to 13. This is not confirmed. This is photometric, so it needs spectroscopy to be confirmed. But yeah, we got to 13, which is a big jump ahead. This in 2016 was the furthest galaxy ever observed. And then James Webb, these are new images, has got a 10, 38, 11, 12, essentially, 12 and a half, and over 13. So we are pushing the boundaries. Right. Again, in the past, from the deep fields, we observed that galaxies were bluer, brighter compared to galaxies of the same mass today, smaller on average, because we said the universe is formed accreting mass, smaller in size, of course, as well, and more numerous, because galaxies increase in size by merging. And so merging causes the decrease of the number of galaxies. Although the new deep field with James Webb showed that some galaxies quite distant in the past look remarkably like modern galaxies. So I leave this open because there haven't been enough studies yet to determine whether our theories are wrong, or what's going on. Why do we have these nice barred spirals so far back in time? Right, so talking about environment, this is what we see. We see our galaxies back in time, different shapes, different colors, and we see this is in groups and clusters mainly. There seems to be a relation between the type of galaxy and where it's found. This is a quite old observation, but it's still the strongest evidence we have for this. It looks like ellipticals are found in the center of galaxies and clusters, mainly clusters, lenticular sometimes, and then spirals are on the outskirts of clusters, or the isolated galaxies tend to be spirals. But morphology is something that requires you to look at each galaxy picture by picture, and it's time consuming. Because we said usually early types are red because they're old, we can use color, and we observe exactly the same situation as we do in star formation rate. So we see that towards the center we have redder galaxies, so no star formation, while the galaxies in the field or in the outskirts are forming stars. So clearly the environment is affecting what happens to the galaxies. Sometimes we see groups falling into clusters, and sometimes we see spirals, which I said earlier were always star forming, not forming stars and being very, very red. So what causes this? Well, these things clearly, these evidence show that environment is probably the main player in the evolution of galaxies. Surely stars will evolve, surely AGNs will happen, but the interactions seem to be the most important thing. Right, we talked earlier about this, so I'm not repeating the internal evolution. The only thing that internal evolution that I haven't mentioned is that morphology can change by itself sometimes, but this is a phenomenon not quite understood yet. We don't know what triggers it, but spirals like ours with a bar, there is this process called bar instability, which at some point disrupts the morphology of the galaxy and seems to lead to the formation of a bulgy galaxy, of an elliptical galaxy. But this is not entirely clear as a phenomenon. Yeah, we saw this earlier. Environmental processes. So how the environment affects the galaxy. I've shown you earlier that clusters of galaxies have a lot of gas within. So between the galaxies, there's a lot of hot gas. This hot gas can interact with the galaxies, mainly with friction-like processes. Otherwise, it can be an interaction between galaxies. Right, so ram pressure stripping is due to the hot gas, and it happens when a galaxy gets accreted by a cluster or a group, and the hot gas literally acts as the air when, you know, when a spaceship comes back to Earth, the friction. It's exactly in the same way. It's seen, so this is an optical image superposed to an hydrogen radio image, and you can see that the contour, so this is dust gas that emits in the radio. It's bent outwards, so opposite to the direction of infall of the galaxy. And this one is again in the this is in the optical mainly, and we can see again gas being stripped off the galaxy. Of course, this is a process that's more effective if the galaxy falls in at a high velocity or if the region is extremely dense. Once the gas has been stripped off, there is no more gas for star formation, and the galaxy, so this also disrupts the spiral arms. So the galaxy becomes just a lenticular galaxy. So no spiral arms anymore, not much going on within. It stays flat though. Strangulation or starvation happens when the velocity is a bit slower or the density is a bit lower. It doesn't strip the gas from inside the galaxy, but it just strips the gas that is around the galaxy, the gas that would have fallen into the galaxy to form new stars. So by getting rid of this gas outside, the galaxy will use what it's got in it to form stars, but once that's gone, that's gone. And so the galaxy will just age. Again, it doesn't change the morphology, and it's a much slower process, but it leads to a lenticular galaxy with no forming stars. Harassment is between two galaxies, and it happens usually when a galaxy passes near either a group or a cluster or a massive galaxy at a very high speed. So this gravitational interaction can disrupt mainly the smaller galaxy, which can lose its morphology or get disturbed. It can formate a bar, it can become oblongate. And what happens is that because the gas gets in some ways disturbed, it can trigger star formation in those areas where the gas gets compressed. Sometimes stars are lost, like they just become wandering stars around the cluster or the group. And because the morphology is disrupted and some galaxies and gas can be stripped off, the spiral will become an elliptical, but a dwarf elliptical, because it will lose mass. Tidal stripping is similar in concept to harassment, except usually the galaxies are similar in size and the speed at which they meet is much lower. So they will just feel each other gravitational force, and the outskirts, especially the gas and the stars in the outskirts, will be affected by that. They will form beautiful long tails, these are probably the best pictures, really. Beautiful long tails. Again, they can lose stars, they can lose gas, and at the same time, when the gas gets compressed, they can trigger starbursts or star formation. Usually tidal stripping is so when two galaxies like these two meet, the tidal stripping lasts, and it has like a yo-yo effect. So the galaxy will pass each other, deforming each other, then get further apart again and fall back in until the distance gets smaller and smaller, and they will eventually merge, which means usually between, from two spirals, we will have the formation of a big giant elliptical. And in fact, we got the merger at the end, which is the result of a tidal stripping. The speed becomes so low that the two galaxies just won't be able to resist each other's gravity, and they will just form one elliptical galaxy. This is the process that leads to the decreasing number of galaxies and the growth in size. During a merger, it's true that we form an elliptical, but in the ongoing process, we can again have a star formation burst. So if we see an elliptical with star forming, with a star formation inside, it's interesting to try and investigate it, because that's probably a quite recent merger between two galaxies. So again, these are probably nice pictures to take.
What does recent mean, Melissa?
Well, recently, so these haven't merged completely yet. Recently, it's a good question. Recently means, oh dear, I don't even know how to give a time in human time, because it's not recently for us. Let's say it's something so a merger event can start shortly after the galaxies were formed. Really depends how close they are, and they can merge at any time. I don't know how recently is. It depends on the distance of the two galaxies, what redshift we're looking. Yeah.
But it means hundreds of millions or billions of years.
Yeah, oh, absolutely. But what I meant to say recently is that recently for those two galaxies, yes, not recently respect to us. So if I see an elliptical galaxy with star formation, I know that galaxy literally just formed. It depends, of course, recently formed, but it could be still billions of years ago if I'm observing a galaxy at redshift 8. If I'm observing a galaxy at redshift 2, is more recent, but in the observation frame, that galaxy just formed. I don't know if you see what I mean.
Yes, I do.
Yeah. So it's not recently in human time at all. It's just that it's a newly formed elliptical galaxy. If we could observe that, I don't know, 1 billion years before, that probably was two galaxies.
Right.
Right. So let's try to simplify the evolution of galaxy. Different processes are fast and external. Some are faster internal. Some are slow and internal, which is star evolution, and others are slow and external, like mergers. Yeah. So one thing to bear in mind again, when we observe galaxies, we need to consider at what redshift we're observing. So what we observe might be completely different now, but if I see a galaxy falling into a cluster that is still star forming, or this still hasn't changed its morphology, or it looks like a field galaxy, I know that galaxy just got into that gravitational potential well, because galaxies are not, the effects of tidal stripping, for example, are not immediate. It takes time for things to happen. And so initially, all galaxies will evolve passively. So just star forming, using the gas they have inside, using the gas that cools down from the outside medium, And of course, again, even when they start being affected, it starts on the outskirts of the galaxy because the gas within is much denser, so it's more difficult to strip away. It also depends on how big the environment, how massive, how hot the gas is, for example, how big the cluster is, or how big the galaxy that falls in. If I've got a massive spiral falling into a cluster, it will be less affected than a tiny irregular falling into a cluster. So this to say that all these processes are ongoing. They have different timescales and different strength based on the conditions. So they're difficult to disentangle, and also it's very difficult to observe only one of them and understand really how long that one takes, for example. So there isn't any agreement whatsoever on what really goes on. And as we also know, if the further back we look, the universe was smaller. So galaxies were closer together, the universe was denser. So surely the efficiency of these effects is completely different at different epochs. Right, so this to say that galaxies are very complicated, and they're a complicated object in a complicated large-scale structure, in a complicated universe. Then there are many processes that affect them, and they're difficult to observe, especially if we want to observe back in time at high redshift. What we know, though, almost certainly, is that galaxy distribution follows the dark matter distribution. There are definitely two types of evolution processes: internal, which mainly are responsible for the evolution of massive galaxies or isolated galaxies. Environmental processes, which affects mainly galaxies that are smaller and they found themselves maybe in a big cluster. We know we've got fast processes, which are more efficient in clusters because there's more hot gas, more mass, and slow processes, which are more efficient in groups or in galaxies that just meet in pairs or small groups. In the past, as I said, is still a major challenge, especially with the new observation that seemed to show a universe that looked incredibly similar to the universe today. And this is not what we expected. Just to finish, James Webb, beautiful images of merging galaxies here. This is the Stephan's Quintet, which is a group of galaxies, what we call a compact group. We can see an ongoing merger here, tidal stripping here. This one is not in the, is part of the quintet, but is not part of the group really. Right, the future. I remember talking a lot about James Webb, but actually, especially for galaxy groups and clusters, the future is on Earth. And it's thanks to adaptive optics, because James Webb is focusing on answering the big questions. And also its field of view is quite small, so it's difficult to observe big clusters. But with adaptive optics, we can actually observe very well from Earth. Adaptive optics are simply, you're probably aware, but they're simply new telescopes where the mirrors can change shape to adapt to the atmospheric turbulence. And so they send out laser that measures the turbulences. The signal returned to the telescope, and the sensor just modify the shape of the mirror to cancel out the turbulence, to have the neatest image possible, as is shown in this image taken with the same telescope, turning on and off the adaptive optics. Yeah, this is Neptune, which is remarkable, really. The two main projects are the Extremely Large Telescope. Just to give you an idea, this is in Chile, and the Atacama Desert, quite high. Big mirror made of almost 800 little small hexagonal mirrors. First light 2027, but that's just technical first light, so I don't know when it's gonna work. The Giant Magellan, slightly smaller and it's a different concept as well. Still adaptive optics, but the mirrors are much bigger. There's just 7. They look both in the optical near infrared type pictures. This is in Chile as well, but it's a bit more south than the other one. This is technical first light 2029, but there's no chance. The funding seems to be frozen for this one, but we still hope that. So they had a project for this one when I went to Chile in 2012, and they still haven't really started building. They just cut off the mountain. Right, sorry. I think I talked too much. Thank you for listening.
Thanks very much, Melissa. Shall we stop sharing so that we can see one another?
Sure.